that a different strategy would be, say, the problem of those postulates is the mention of physical states of microscopic systems. And it would be more appropriate to eliminate that from the postulates and describe everything in terms of measurements, but also preparation procedures and transformation procedures, and concepts that are sort of everyday concepts, things you can understand at the macroscopic level, so descriptions of experiments. And so today we're going to continue with this strategy, the operational strategy. And we're going to, in the course of today and the next lecture, try to reformulate those postulates such that they do only refer to these operational concepts. Okay, so the idea is going to be that elements of the formalism of quantum theory are going to correspond to experimental operations. And more precisely, think of an experimental operation as kind of a recipe book. It's a list of instructions. So what's a measurement procedure? It's kind of a recipe. It says, build the apparatus this way, set things going, register the outcome, tune the magnetic field to this strength. All of that long list of instructions is what I mean by the measurement. Okay? And so the idea is going to be that the formalism, the elements of the formalism are going to represent those sorts of lists of instructions. Okay, so let's go back to this simple example of an experiment, the Stern-Gerlach experiment, where you have an oven here that puts out, say, neutral silver atoms with an aperture. And then you've got your inhomogeneous magnetic field, which splits the beam and sorts it depending on the spin. What I want to do is sort of abstract away all the details of this experiment. So I want to be able to talk about any quantum experiment where you prepare something and then later you measure it. So to do that, I'm just going to sort of introduce these cartoons. This is just going to mean some preparation procedure. So over here, it's this box here, which prepares these neutral silver atoms. But it could be much more complicated. I could do some filtering first before I send it through this experiment. And all of that sort of processing, I'm going to imagine, is sort of sitting inside this box. And this is an output aperture, and the system comes out of that, and it's ready to be measured. And this little button on top just sets things going. And then meanwhile, I'm going to abstract away all the details of the measurement procedure and just represent it by a box that has an input aperture, takes in a quantum system, and then has a little pointer that reveals an outcome. And for different sorts of measurements, you'll have different outcome spaces. Sometimes it's discrete, sometimes it's continuous. But that's all I really need. I'm not going to be talking about particular sorts of experiments. Now, an operationalist would say that what you really need is an algorithm that tells you for a given list of instructions that describes a preparation procedure, and a given list of instructions that describes a measurement procedure, what a theory should do for you is predict the probabilities of getting different outcomes in this measurement for that preparation. And that's all it really needs to do. It needs to correlate things. So it needs to provide probabilities for k given the descriptions of the preparation and the description of the measurement. And so you can formulate quantum mechanics that way. The idea is that the preparation procedure is represented by array and Hilbert space. So now, rather than saying array and Hilbert space is a complete description of the properties of some physical system, we're saying, no, array and Hilbert space is just a representation of a list of instructions of what to do in a lab that constitutes a preparation procedure. For every preparation procedure, there's a different array and Hilbert space. And you kind of think of it as a kind of a catalog of expectations. This mathematical object will tell you the probabilities for the outcome of any measurement you might do following on this preparation. That's its role. And over here, if you want to calculate the outcomes of the measurement, you represent the measurement procedure by a Hermitian operator. And if this is the spectral resolution of the Hermitian operator, so the pi and k's are the spectral projectors, then the algorithm for calculating these probabilities is just take the expectation value of pi k for the ray psi. And that'll tell you the probability of outcome k. So here we're thinking things really differently. These are just, again, tools we use to extract probabilities for any sort of experiment. Okay, so that's the kind of a very minimalist approach to interpreting quantum theory that the operationalists would use. Now I want to make a few comments about Hermitian operators. I'm not sure how many of you sorry, question first, or? Yeah.
Yeah, I have a question about something on the previous slide.
Ah, yes.
See, in the bottom formula, or actually before that, first you said that we would represent a preparation procedure by the right side.
Yep.
And in the bottom formula, we're also representing the preparation procedure by P, but the formula contains both P and psi. So in that formula, both P and psi are supposed to represent the preparation.
You can think of it this way, that the left-hand side is what I'm interested in. I have a description of the preparation and the measurement. I want to assign probabilities to these different outcomes. And now the formalism of your theory is supposed to give you an algorithm for computing this. So what it says in the case of quantum theory is that for every preparation P, there's some ray in Hilbert space psi. So I could have written psi sub P. And quantum theory provides a kind of mapping from preparations to rays in Hilbert space. And so then here I have a psi sub P and a pi sub M. So it would tell me that as I vary P and M, these probabilities might change because psi varies with P and the sets of pi's vary with M. Now typically there's a lot of details of the preparation procedure that don't influence what the ray is. And so, for example, say over here, there's many ways I could measure the polarization of a photon, for instance. I could use a piece of calcite crystal, I could use a piece of Polaroid, I could do all these things. So there's a large set of measurement procedures which are very different, all of which are represented by the same Hermitian operator. That issue, the map between the measurements and the preparations and their representations, is going to come up next week in the context of contextuality and the Cauchy spectral theorem. So I wanted to make just a few comments about the representation of measurements. And as I said, I don't know all of your backgrounds, but often in undergraduate quantum theory, there's a heavy emphasis on Hermitian operators and calculating the expectation values of Hermitian operators. And I just want to emphasize here that actually all that's... This is the meeting I'm missing. There we go. All that's really relevant is that is these spectral projectors for calculating the probabilities. The eigenvalues don't appear in this formula. So in particular, if the spectral resolution of this Hermitian operator has only rank 1 projectors, so there's no degeneracies among them, then I just plug in that projector. This is the formula, and of course that's just the familiar form of the overlap of psi and phi k mod squared. And if there is degeneracy, so if there are many different rays here labeled by j that all have associated the same eigenvalue, ak, then this is the projector, and I just have to sum over that degeneracy index j when I'm calculating the probabilities. But the eigenvalues don't appear here, and so they're really just conventions. So in your undergraduate courses, you probably spent a lot of time calculating expectation values for Hermitian operators. So this would be the formula here. So you take the probability distribution, you average these eigenvalues. But when you ask, what's inherent to a measurement device, it's really the probability distribution over those outcomes. How I choose to label those outcomes is sort of irrelevant. It might allow me to say something sort of generic, like, what's the mean position I measure? That might be a useful quantity. But ultimately, if I tell you the probability distribution over outcomes, I've told you everything. And two Hermitian operators that are different might be associated with the same spectral projectors. They might only differ in their eigenvalues. And then those two Hermitian operators can be measured using exactly the same device. Okay, so it's not as if for every Hermitian operator there's a different measurement device. It's actually equivalence classes of Hermitian operators that are associated with different devices. And the equivalence relation is they need to have the same spectral projectors. And the eigenvalues are just a conventional way of describing and labeling those outcomes. Okay, so as I said, I find this isn't really emphasized in the textbooks. But one way to to make it clear, is that instead of associating measurements with Hermitian operators, you can associate them with what are sometimes called projector value measures or projection value measures. So just the set of projectors that appear in the spectral resolution of your Hermitian operator. So as I vary this object, I do vary the sort of measurement I'm talking about. So if for any two different projector value measures, I will get different statistics for some preparation procedure. So they're really different measurements. This is the norm in quantum information theory. We talk about PVMs, not about Hermitian operators. And for most of this course, I'm going to do the same. I'm going to be talking mostly about these objects. One other small note is that the term projector value measure really is a bit heavy-handed in this context because I'm assuming that this outcome space is just a discrete set. Outcome 1, 2, 3. This terminology was introduced when people were considering outcome spaces that were continuous sets. So if you're doing, say, a measurement of position, so now you've got the real line as your outcome space. And then you can really associate, the right thing to do is associate a map from the algebra of subsets of that set to the projectors. And that thing, that mathematical object is called the projector value measure. Here, I think it's just, I'm going to take the easy way out, always use discrete outcome spaces, and then it's just a set of projectors. But for some reason, this terminology is kind of stuck, and we still talk about these things as measures, even though they're really just sets of projectors. So hopefully that won't be confusing. Okay, what about evolution? So in the standard picture, the realist picture, we have Schrödinger equation, we have Schrödinger evolution. We have a particular way of thinking about that as a law about how the properties of systems are going to change over time. But an operationalist doesn't have systems and properties. They just have, they're trying to make predictions about experiments. So in that context, the way you think about evolution and unitary maps is just a way of representing a transformation procedure. So a transformation procedure is just a list of instructions that corresponds to something you're doing in the lab that comes between a preparation and a measurement. So for example, it could be when the electron comes out of whatever preparation procedure you've done, put it through a magnetic field of this strength before setting up your detection screen. So that's a particular kind of transformation procedure. And as you vary, say, the strength of the magnetic field or the time you let it propagate, those are all parameters in your transformation procedure. And the idea of the operational approach is that what unitary maps represent are those transformation procedures. And that's all they represent. So the algorithm now has to specify, for a given preparation, transformation, and measurement, what are the probabilities of the different outcomes over here. And the way quantum theory does that is just by saying, take the unitary, act it from the left on side, and act the adjoint of the unitary from the right on side in this formula. And that will give you probabilities. Okay, now, it's clear that you can always lump this transformation in with the preparation procedure. So remember, the definition of a preparation procedure is just some list of instructions, what to do in the lab, where there's kind of a notion of that gets things started. Like, there's a button that begins the whole process. And so if I put a box around both these guys with an output aperture, that certainly qualifies as another preparation procedure. I'll call it P prime. And there should be a map. If I know that this preparation is associated with array psi, and I know that this transformation is associated with the unitary U, well then the effective preparation is just U psi, which I'll call psi prime. And if I use the old Born rule, right, the old algorithm for calculating these probabilities, but now applied to P prime, it would just tell me this, and that reproduces the formula from the last slide. Yes?
What is the benefit of viewing the transformation as part of the preparation procedure? Why bother taking this point of view?
Why bother taking this point of view? I guess because, for one, you'd like your representation of preparation procedures to be appropriately closed under the right set of mathematical operations. So you could say, whatever the set of preparation procedures are, they're going to include preparations like this. So the way I represent transformations and preparations are constrained by the fact that this is an effective preparation. I guess also it's a consequence of how we're doing things here. That if you really think that vectors in Hilbert space represent preparation procedures, then there's nothing important about sort of this preparation procedure as opposed to this one. They're equally valid as sort of fundamental concepts in the theory. And there's one other fact, which I'll mention in just a minute, which is that you can also lump this transformation procedure together with a measurement device and call this whole thing an effective measurement. And it's the same sort of deal. If I represent this measurement by the projector value measures corresponding to the set of pi k's, then I should represent this effective measurement by this conjugation by the unitary of pi k's. And of course, if I do that, I'll get exactly the same formula for the predictions. So is this duality familiar to you? It's not. This is probably not the way you saw it, but yeah.
Schrodinger and Heisenberg.
Exactly. For the operationalists, the distinction between the Schrodinger picture and the Heisenberg picture is just a conventional choice of whether you want to consider your transformation procedure to be part of the preparation or whether you want to consider it to be part of the measurement, and nothing more than that. Now, it's possible to do a measurement wherein the quantum system survives. So I just put an output aperture here on my measurement device. So now this device not only generates a classical outcome k, which is where the pointer is pointing, but it also generates a quantum system that's left over after the measurement's done. And so if I put a box around all this, then again, that satisfies the definition of some effective preparation. And so there should be some ray in Hilbert space that describes that. And so you need an algorithm that maps you from the ray that represents the preparation, the set of projectors that represents the measurement, to the ray in Hilbert space that's going to represent the effective preparation when outcome k occurs here. And that algorithm is just the familiar collapse rule, the von Neumann projection postulate, that if psi is the ray and the pi k's are the projectors, then the ray you associate with the effective thing is just the projection of psi into the pi k subspace normalized. So the status of the collapse rule here is not some kind of change in the discontinuous change in the physical properties of a system, but again, just an algorithm for computing probabilities of outcomes of measurements that are going to come in the future of this device. Yes?
And how does one distinguish transformation from a measurement?
Well, the measurement also has some classical outcome k, whereas a transformation doesn't. A transformation, in a sense, is deterministic. It always occurs. Whereas here, for every value of k, you have a different transformation happening. So what you can do is you can think of these as a set of non-deterministic transformations. One for every value of k. And if I, for example, don't know what outcome k occurred, and I average over all those possibilities, then the average is a transformation, because it always happens. One of those outcomes always occurs. So we'll get to this probably next time, the most general way of representing a transformation procedure. So far, we're looking at sort of a small subset of the transformations and preparations and measurements, those that are associated with unitaries and with projector value measures and with rays in Hilbert space. But I wanted to start with this sort of simple version because it gives you a clear idea of what a strict operationalist would say about the quantum formalism and how we should interpret it. And the question I want to ask you is, before we move on to developing this operational framework, should we be satisfied with this? So suppose somebody said to you, here's a minimalist way of interpreting the quantum formalism that won't get you into trouble because you're not going to make any claims about the properties of systems and you're not going to run into any no-go theorems. But more than that, I think that that's all we need. That operationalism is the end of the story, and this is the interpretation of quantum theory that we should adopt, and we shouldn't look for anything more. Would that be fine with you, or do you think that there's a problem with that? Sure.
I intuitively feel two objections. In one sense, it's hard to see how you would advance beyond it then.
It's hard to see.
It's hard to see how you would then improve your theory if you strip it from more conceptual picture, because then it's hard to know where to tinker to change your theory. And secondly, the second point is more vague because I can't make it exactly, but the feeling that it's hard to check whether it's a consistent theory, because you remove all the interrelations between concepts in the sense that one measurement device typically consists of multiple measurement devices, and it seems that the same situation can be analyzed in multiple ways depending on how you look at it, and it's not clear to me that then gives you consistency. So yeah, sorry, I can't make it. It's just simply put, for me, I think it would be harder to check consistency if you have less conceptual picture, because it's harder to reason about.
It is true that because the sort of conceptual framework is really sparse, and you don't have a lot of concepts that the realist would have available to them, it does make it harder to do the first thing, to kind of, how do you extend your theory? Do you have, what are your good ideas for coming up with some other theory? It does allow for some kinds of generalizations, though. Sometimes it can be liberating to be an operationalist, because by doing this, you free yourself of a number of preconceptions of what's going on that your realist picture brings with you. So a good example would be when Einstein developed special relativity in 1905. He was using a very operationalist approach. He was trying to define the notion of synchronization in a totally operational way. What does it mean for two things to be synchronized? Well, the hand of my watch and the hand of the clock on the wall are going to coincide. And he was able to see beyond the old picture of space and time that everybody else sort of just took for granted by trying to be strictly operational in his description. So in that way, it can sometimes help you make progress. But I agree that it's, in a way, it's an extremely conservative approach. It doesn't stick its neck out. A realist might say, I have a crazy idea about the world being made up of funny new kinds of things evolving in a different way, and that might make predictions that are easy to falsify. And so that kind of theory sort of sticks its neck out and could be easily falsified. Whereas I would say generally these sorts of approaches are more conservative than that. And so in a sense, yeah, it's harder to know where to go in an operationalist approach when you're trying to develop your theory. Yes?
So it seems like we have a few fundamental classes of objects here. We have things that evolve a quantum state without spitting out any classical information into the environment, right?
Yep.
And that would be the transformation. Then we have some measurement devices that leak classical information out and forward some quantum state that's not the same as what came in.
Mm-hmm.
And then we have measurement devices that just give you some classical information and don't forward a quantum state at all.
Right.
So we have these three sort of classes of objects that exist, but then it's not entirely clear, like, what is sort of determining whether a measurement device leaks information out, or what's special about the ones that forward a quantum state without leaking information.
Yes. Are you wondering why we have just sort of these kinds of primitive concepts as opposed to others? Or are you saying what criterion does the operationalist apply to decide how to represent a given experiment?
Yeah, like sort of how do you know a priori, I guess, whether you're going to, yeah, how to classify everything?
Well, the latter question I think is sort of evident from what you're doing. So if I am, say, detecting photons in a photodetector, that's a process where, so I might learn something about, say, the number of photons that came into my detector.
Yeah, no, I mean, I guess what I'm saying is,
yeah,
no, I mean, I guess what I'm saying is you can have something going on in a lab where you don't realize that you're leaking classical information out to the environment, but you actually are without knowing it. You know what I mean? Like, you think you should be performing a transformation, but like if you're just sitting in the lab, you're not omnipotent. You can't necessarily tell, everything that's going on and all the interactions are happening. So how do you know if you're forwarding a quantum state out the other end or you're leaking?
Well, I think we can basically say that what we mean by what the operationalist means by the outcome of a measurement, okay, is really what they have access to. So if there is some outcome that the environment has access to, but the experimenter can't resolve it, then the experimenter will not condition on K. So when the experimenter says, what should I use to make predictions about some measurement down the road, they're not going to use psi K because they don't have knowledge of K. They could use some coarse graining of K. So imagine that this is a very large set, but the experimentalist only learns sort of in which subset of this large set K lies. So sort of like a coarse grained version of K. Then for them, they're going to, let's call that K prime, the coarse grained version of K. They're just going to learn K prime, and they're going to condition on K prime. So they're going to describe this whole thing, after they've observed K prime, as some effective preparation pk prime. And they're going to associate a vector psi K prime, which is associated with the projector, onto the K prime space, which is now a sum of projectors for all the Ks corresponding to that value of K prime. So the idea is that you should think of this K as like the variable that you condition on in classical probability theory. So an agent learns some information, updates their knowledge about something else. Similarly here, we assume if an agent learns something about the outcome, then this is how they update their knowledge. But if there's classical information that they don't learn, then they can't use that in this rule. So in this sort of approach, this update map here has the kind of flavor of Bayesian conditioning, kind of thing you do in classical probability. You learn some information, you change your predictions, you change the object you use to make predictions about measurements down the road. So already the operationalist, in a way, is starting to, because these quantum states are representing a catalog of expectations of what you're going to see in the future, the change here is now has more of the flavor of Bayesian conditioning, a change in your knowledge, than it does a discontinuous physical change in the world. So other comments on operationalism as a philosophy of science? Yes?
I'm not sure if I understood it correctly, but it seems to me that there's no basis for any form of operators that you construct for an operational point of view. Like, there's no physical basis. You kind of construct operators just so that you match your experimental results.
Right.
There's no basis why an interaction should be given in this form, because you're just trying to reproduce your data from.
Yes.
Is that how?
That's right. And this is part of the tradition, the philosophical tradition in which operationalism is embedded, I would call empiricism. And Ernst Mach, for example, was an empiricist. And he famously said, it's wrong to think that the business of science is to explain why objects move the way we see them move. It's the business of science to explain how they move as efficiently as possible and as precisely as possible, and leave it at that. And he thought that this attempt to come up with reasons why was sort of a negative force in science, because it led people to do a lot of metaphysics and speculate and talk about things that you couldn't really verify. So from his view, astronomy should be about providing a description of the motion of planets, not some sort of account of why they move in the way they do. So you're right that this should feel like that because that's what the empiricists wanted, just a description of what was going on.
So, I mean, that in principle, then that means you can have, as long as you get the same results, you can have, in principle, you can have more than one possible way of writing the operators, more than one possible mathematical construct of the entire theory, actually.
Yeah, I guess the operation would say as long as you get the observable things right, here the relative probabilities of the different outcomes of the measurement, two formalisms give you those same probabilities, then they're equally good descriptions. Yeah. So I should say that one of the motivations that the empiricists had for trying to merely describe phenomena was that they were really interested in trying to have certain knowledge. So the problem is if you speculate about unobservable entities, then you might make a mistake. And their idea was that if you only describe, only make claims about things that are actually observable and accessible to you, then that's stuff you can't be mistaken about. So, a radical example would be if I see a patch of green in my visual field, well, I can't be mistaken about that. And so if I base all my knowledge on claims like that one about things I've observed, then I can have certainty. And I can stay away from metaphysics that might be mistaken. Yes?
But if we want to make the description of this huge catalog of data that we have efficient, as we said, wouldn't that require that we introduce, for example, concepts from other areas of knowledge at some point and just make some sort of an interpretation?
Can you tell me more? What exactly do you have in mind about an example?
I know you might need, for example, mathematical functions or such. I feel the line between describing the data efficiently and making interpretation might be blurred.
Yes, I think I know what you're saying. Let me give maybe an example that I think this is what you're trying to get at. So there was an American Nobel laureate physicist from the 20th century called Percy Bridgman, who wrote a book. I can't remember what it's called, but it's basically about an operational approach to physics. And he was shocked that special relativity showed that we were radically deceived about the nature of space and time, and that there were sort of multiple different ways of measuring length. And he thought that it should never happen again that we have that kind of revolution where we find out we were so radically wrong about something. So he thought that the way to avoid that happening again was to make sure that instead of imagining a concept of length being defined in terms of physical properties of systems, he said we should define our concepts in terms of experimental procedures. So if, for example, if you want to measure the length of a streetcar, one experimental procedure would be hop on a streetcar, lay down your meter sticks. That's one way of measuring the quantity. So let's call that length. And now another way of measuring some quantity is to maybe measure the speed of a streetcar and find the time it takes, find the time when the front of the streetcar passes you, or the time when the back of the streetcar passes you, and calculate a length quantity that way. And so Bridgman says that those are two different concepts. And if we had done science in that way, we would have known that equating those two experimental procedures, those two quantities, was a leap. It's not necessary that you have to equate those. We wouldn't have assumed it. And so in that way, we might have discovered special relativity earlier by, considering the possibility that those things were different. But the problem with that people have pointed out is that it's unclear where you should stop. What details about how I do the experimental procedure are actually relevant? How many different concepts do I need? There's all sorts of small details about how I measure the length of the streetcar that could be relevant and could form a totally new concept. So I think an appropriate response to Bridgman is that without some abstraction, without throwing some of these details of the experimental procedure away and saying all these things are measuring the same quantity, you really can't get very far in science. You just, you have too many different concepts. And it seems to me that's maybe similar to what you were saying about trying to get an efficient description. So does that mean the rest of you are all right with operationalism? Or? Yes.
I'm just wondering how you define when a preparation starts to be prepared. Because you have to give your experimental apparatus something to prepare. So you give it a state, it prepares it, and then sends it off to be measured. But that state that you have to give it was prepared by something else, which was prepared by something else as well. So is your preparation the entire history of the universe?
It reminds me of the problem of priors and probability theory. How do you know what probability distribution to start with before you begin to update it? So in many cases, you can say that there's kind of an assumption of a Markov process, that there's certain ways of preparing things where it kind of becomes irrelevant what the history is. So if I subject a particle to a lot of filtering, then by believing quantum theory, I might come to the conclusion that the quantum state I should assign to this particle is independent of what the state of the particle was prior to my filtering process. And therefore, I don't need to know what the state of the particle was earlier in order to know what state I should assign it at the final time. So as long as I know that the list of instructions of how to prepare the particle is of that sort, which kind of screens off the past, then I know what state to assign. If it's not of that sort, if it doesn't screen off the past, then I'll go looking for information about what happened earlier. But even if I don't acquire much of that, I can always just do averaging, right? I can say, well, look, I know it was one of these things, but I don't know which. I know what quantum state I would have assigned for each of those, and I'm going to average over them. And so I might have a state that, as we're going to see later today, is highly mixed, not a pure vector and Hilbert space. I'll still have a state to assign. And in the worst case scenario, I assign what's called a completely mixed state. And that basically says, I don't know anything about this system. I haven't a clue. And it means that every measurement is totally unpredictable to me, because I don't have the least idea what's going on with this system. So even in those cases, you have a well-defined prescription. Yes?
If you're trying to figure out where to start when describing your preparation procedure, and if your preparation procedure is a list of instructions, then could you choose to start your preparation procedure with the materials that are available to the particular experimenter that you're writing your experiment instructions for, and say, take this particular piece of metal and this particular, put them together in such and such a way, and that's all you need for a description of preparation? It depends on what's available in your laboratory.
Sure. Yeah. I guess even then, you could ask the question of, what if you knew more? I mean, I suppose any description of a preparation kind of assumes a lot of background information. So when I say, go and take a chunk of silver and heat it up, and then let some of those atoms come out of an aperture, I'm assuming that we can agree on, what a chunk of silver is and how to do all these things. So in a sense, we presume that we speak a common language, and I can describe an experiment to you accurately. And even if the way you implement the experiment is different from the way I would implement it, as long as those differences are not things that we're conditioning on. So again, we can sort of average over certain features of the experiment that are not explicitly referred to in that list of instructions. And then we might get a quantum state that's not quite as pure as it would have been otherwise. But we can still have a procedure that has a well-defined quantum state associated with So I am interested in getting back to the question of what you think about the dichotomy between realist approaches to interpreting quantum theory and operational approaches to interpreting quantum theory. I'm sort of curious, are you guys realists? Do you think there's something wrong with the operationalist approach? Or are you happy to say, yeah, this is all there is to quantum mechanics, and we shouldn't seek to describe systems in terms of properties or explain why the statistics are the way they are? Yeah.
One sort of general question about this whole framework. Are we assuming that this whole thing respects things like translational symmetry across the universe, such that if an observer on, the other side of the universe were to carry out the same experiment we did, that they would get the same results? Like, is that embedded?
It's not an assumption of the operational approach, but that fact about the universe could be expressed in the operational approach. You could say, if you do the same experiment, follow the same recipe here or there, you will get the same statistics. So I've just described things entirely operationally, and I've expressed a kind of translational invariance. Whereas if it was a failure of translational invariance, then I could say, that operation, that experiment which tells you to do it here, and that experiment which tells you to do it there, well, here and there are part of the list of instructions how to do it. And it could be that my theory says, and you're going to get different statistics depending on when you do it, and how you represent the preparation, the vector you use, could well depend on where you're doing that procedure. So it has the capacity to express either sort of
Okay.
that.
And similarly, what happens with something like time reversal symmetry in an operation?
That is a good question. Definitely you'll have a different attitude towards time reversal if you're an operationalist than if you're a realist. So a realist might say, there's a kind of time reversal symmetry in my theory, which is that if you played a movie of the universe backwards, so let's say I have a model of the universe involving particles moving in the void, and I might say, look, if I play the movie backwards, you'll see that that's also a valid evolution. It's consistent with the dynamical laws. The operationists can't do that because they don't have particles and moving away. But the operationists can do something else. They can say, so let me just give you one example of a kind of time symmetry. Suppose that, let me just go a little bit further back. Suppose that you had one of a set of preparation procedures that you were interested in. So I have these little knobs on the devices, which means that sometimes you can sort of choose one of several different preparations. So say I had an index j, which specified which of these preparations I'm doing. And I have this outcome k over here. I could calculate the probability of k for every j. And I could say, all right, now let me find all the kinds of conditional probabilities like that my theory allows. But now there's another kind of conditional probability I can calculate, which is the probability of j given k. So if I know the value of k, what can I say about the value of j? Maybe I know it precisely, or maybe there's some facts about it. So if you found that the probability of k given j, for every experiment that has a certain probability of k given j, you can find another experiment where the probability of j given k is exactly the same. Well, that's a kind of time symmetry. So you have alternative ways of talking about those same sorts of concepts. Truthfully, I think that the question of time symmetry in an operational approach is something that people are still working on today. I wouldn't be surprised if in the next year or two you saw some papers on the archive on that very sort of question. I'm still waiting for somebody to take a stand. I'm expecting some of you out there might be realists and unhappy with the sparsity of this sort of approach.
It doesn't actually tell me how I get the classical result k out of my measurement box. So the problem is I could regard my measurement box as a preparation itself because it is a quantum system. So, I mean, ideally, I want to know how I get that result k out of this given preparation. That's one issue I have.
So when you say, how do I get the outcome k, you're saying it's not enough to have an algorithm that predicts the relative probabilities of those different outcomes. You want something more than that? But what more do you want?
I don't know, I guess my issue here is coming partly from the fact that I guess that there are so many different algorithms to get it. Because the measurement box is a preparation as well.
Right.
So you can't distinguish between the two.
Well, I should say that the way you represent the measurement, if you want to predict the outcomes of this measurement here, then you represent it by a set of projectors. If you're interested in something else, right, so let's move forward here. If you're actually interested, I haven't drawn it, but there's, say, another measurement that comes in the future with outcome L. And what you're really interested in is making predictions about those guys, the L's. Well, then you associate with this measurement preparation a set of states that depends on pi's, but also depends on psi. And so it's, this is associated with this measurement procedure. It's a catalog of expectations of what's going to happen later, whereas the pi k are a way of predicting the outcomes you're going to get for this very measurement, not some future measurement. Yeah.
Well, to give you what you want, I would indeed say that I would prefer a realistic view, and not per se for philosophical reasons, or in the sense that not being satisfied with an operational view for its own sake, but because I think it's more efficient to have a realistic view, in the sense that it is more practical.
More practical.
Well, that it has practical consequences. For example, because it sticks out its neck, as you say, or because, in the sense that she talked about sometimes concepts being efficient to see links and etc. That's it.
Yep.
Oh, I mean, largely, I see that both have their benefits because, like, well, on the one hand, what Ruben says is true, but our understanding of the world might be incorrect or might have some details that are incorrect. And if we base everything, our construct of theory based on what we think should be correct, we are restricting ourselves of exploring what might be possible to be a true description of the experiments, for example. Right? In which case, as operationalists, you are uninhibited by any form of pre-assumptions about what you think should be. So you can kind of like you're not restrained to explore anything, which then later, I guess, as a realist, you can then take to analyze and make sense out of what an operationalist might come up with. I guess both should be working like hand in hand.
I mean, there's a sense in which the realist is also free to postulate whatever crazy things they want to postulate. I mean, they might be held back by some preconceptions they have, as was the case in 1905 with space and time. But it's conceivable that a realist could also sort of get beyond those and think about a different way that things might be, in a different sort of style from what the operationalists would do. If you look at the historical record, the scorecard, how have the realists done, how have the operationalists done vis-a-vis innovating theories, it seems to me that the score is kind of even. So on the one hand, you have the atomic hypothesis. So in the 19th century, chemists in particular argued a lot about atoms. So people had various ideas that they could understand chemical reactions in terms of the notion of an atom. And the operationalists at the time, including Mach, said, no, it's inappropriate to talk about these unobservable entities, atoms. All, the proper subject matter of chemistry are, relative concentrations of different things. How much of a product did you get out of a particular reaction? That's the set of concepts you should use to describe chemistry. And in that case, it seems to me that the operationalists clearly lost that the notion of atoms turned out to be the right way to understand chemistry. And then in the early 20th century, with special relativity, that's a clear example where people's ideas about space and time were holding them back, and Einstein's appeal to operationalism was able to get, make a big step forward. If you look at quantum theory, then it's interesting because quantum theory is born of two traditions. You've got Heisenberg on the one hand with matrix mechanics, and if you look at Heisenberg's original paper, he's very operationally motivated. He says in his paper, all I'm interested in, I'm not interested in Bohr's model of the atom and trying to think of the atom as a planetary system. All I want is a formalism for predicting the frequencies that we observe in atomic transitions. That's all I'm looking for. And by doing that, he was successful. He made some headway. Schrödinger, on the other hand, was not an operationalist. He was thinking about De Broglie's ideas, and he was thinking about waves as real physical things. And he developed wave mechanics in parallel with matrix mechanics, using these realist equations. And in the end, people saw that those two approaches really amounted to the same formalism. So in the case of quantum mechanics, I would say it really was born of both sorts of approaches. So anyways, my view is that it's hard to really say that one or the other is better, methodologically speaking, for making progress. So anybody else? Yes.
Can I just clarify something?
Sure.
So, under the operationalist philosophy,
Yeah.
I mean, so given your previous example, for instance, on measuring length,
Mm-hmm.
right?
Mm-hmm.
I mean, how do you even define the concept of length? Because okay, for example, you might say the length of the car is, you do some procedure, you measure the length of the car, fine. But then that idea of length wouldn't be the same as the length of an atom, right? Because there's no way that you can, let's say, take a ruler and measure the size of an atom. So how can you even make the statement that the atom is smaller than a car? I mean, yeah, how do you, as in, no, I don't see how people can even go beyond that. Like, how do you even define the concept of length in that case?
It's a good question. I would guess that they might say something like, there are schemes for measuring length that might apply at many length scales. Like, what is the time it takes light to propagate across that distance? That sort of thing. So maybe I could imagine an experiment which uses light to try to find the length of an atom. And then also use light to try to find the length of a streetcar. And then maybe the operationist would say, and furthermore, all the experiments I've done thus far, which involve laying down meter sticks after getting on the streetcar and doing this light experiment, seem to show the same results. And so for the time being, I'm going to have a theory wherein those two concepts are equated. But I'm open to the possibility that in the future, somebody's going to show that this light measurement technique and my meter stick technique give different results. And then I'm going to realize that there's really two concepts.
Right now I'm confused, but wouldn't operationalists say refuse to talk about the length of an atom? Because
yeah, it's a good point. If the atom were sort of operationally well defined, like let's say I'm using a scanning tunneling microscope and I have sort of resolution sufficient to see atoms, then I might be able to talk about an experiment that measures that size. I mean, back in the 19th century, they didn't have access to atoms. In a sense, these days we can almost observe them using things like STMs. But this does bring up a criticism that people have made against the operationalist approach. So the logical positivists, which was sort of a school of philosophy science at the beginning of the 20th century, they were operationalists. Well, they were certainly empiricists. They have more in common with the operationalists than the realists. And they were really of the view that we need to make this distinction between observable and unobservable. And if you have a theory which refers to unobservable entities, then there's a project to translate the claims of that theory into claims about observable entities. So their view is when somebody says, the electron has a certain mass, for example, what that really means is a long list of statements about observable things. Like, if I set up an experiment of such and such a sort, then I would observe this. And if I set up this other experiment, then I would observe so-and-so. And they took that to be, the meaning of a claim about electrons is really just this claim about observable entities. Now, the response to that is that it turns out to be very hard to make a distinction between observable and unobservable. Because if you say, all right, things that I can see with the naked eye, well, those are observable, Well, then what about things I can see with glasses? What about things I can see with a magnifying glass? What about things I can see with a microscope? What about an electron microscope, a scanning tunneling microscope, a particle accelerator? Now, like everyone, there's a sort of whole spectrum of prosthetics to vision that get you to see lower and lower. And so at what point do you say, oh, now we've passed from things that are observable to things that are unobservable? Yes?
One might also argue that human vision isn't exactly the most reliable method of observation to take as a sort of primitive in this process.
Sure, yeah. Oh.
It's interesting that Mach said that the goal of science should be to explain how things occur.
Yes.
I was thinking about how an operationalist would explain how some results of a measurement is generated. So one could say that my preparation box makes a preparation, my transformation box transforms the preparation, and my measurement box makes the measurement. That's how measurement value is generated. But I'm not sure why the explanation of how should be at that level of depth rather than deeper. So we could start talking about how the transformation box involves a magnetic field. But we can keep stepping down to greater depths of explanations of how. And if the operationalist truly wants to explain only how and entirely how a measurement result is generated, then maybe the operationalist would need to appeal to concepts other than measurement boxes and transformation boxes.
Yeah. So two things. One is that I think if Mach tried to comment on quantum theory, so when Mach said when he described how astronomical bodies move, he didn't really mean how in the sense of find the mechanism that supports it, but rather just give me an accurate description. In the context of something like quantum theory, that would turn into give me a description of the conditional probabilities for seeing something here, given that you saw something over here. Like that's what the operationist would look for. So it's not so much the emphasis on those probabilities arose because I combined these components together, but just the business of our theory is to predict those probabilities. The probabilities have the same status as the particular motions of planets. They're kind of the data of our theory that we need to reproduce. But the other thing I want to say is that one reason that I personally would provide in favor of realism against operationalism is that an operationalist will have to say that if somebody wants to provide any kind of explanation, then an operationalist should say, well, the primitive concepts, like the positivists said, the primitive concepts should be things that we observe. And so, at the end, your explanations are going to have to end with statements about what we observe. And they saw that as a plus because you can't be mistaken about those sorts of claims. But Popper, I think, argued convincingly that ideal of trying to never make a mistake is just a bad motivation. That basically we should be fallibilists. We should admit that there's nothing we can do to be certain, and instead we should just make bold conjectures, and when they're falsified, reject them and replace them with something else. And that's the way epistemology works. That's unfortunately we're forced to just have false beliefs and improve them as we go along. And secondly, the claims that positivists would take as primitive, like the detector in my lab went to click, that strikes me as the kind of thing that shouldn't be primitive, but should see it's some kind of thing that you should be able to explain. So I should be able to say, why are there detectors that don't click in the first place? Why is there anybody here to build detectors? And why is there a planet that supports life and the sun and all that kind of stuff? And science tends to try to answer those questions. Just gives a long story about maybe natural selection and the origin of life and stellar evolution. And far enough back, gives you a story about cosmology. And it's very unclear how an operationalist could describe all of that part of science. Things like the origin of life, and stellar evolution, and cosmology. Anyhow, why don't we end it there. And I didn't get around to talking about density operators, but that's where we'll start next time.